All right, so along the San Andreas Fault, we have all these earthquakes. And the first thing you're going to do here is name the plates that are on each side of the fault in this map. With the fault coming right through here, it's showing the separation with these arrows. The way geologists show the movement on a fault is, can you tell that's like a half an arrow pointing in one direction and a half an arrow pointing in the opposite direction? That is the standard mapping symbol for the direction of movement on a fault. So you're looking for the plate names here. Here's Los Angeles, San Francisco. You can see the fault kind of goes between them, and it's right between two plates. The other thing on this map is that we have marked three different types of rock. The Quaternary rock, the Pliocene and Miocene rocks, and Cretaceous rocks. So these rocks in green, marked with a K, were formed when there were still dinosaurs here. Remember, on a geologic map, if it's listed towards the bottom, it's older. The youngest rocks are the ones at the top, and we're still in the Quaternary period today. All right, so hopefully you found the names of the plates from the map. Pretty straightforward. So our lab is actually going to be trying to find out how much the plates are moving along this fault. So we can estimate the average yearly movement. We're looking at the average movement, not at any one moment in time. We can estimate the average yearly movement along the fault by examining rocks that have been broken and separated by fault movements. We call this separation the offset of the fault. The map has a good example. The Pliocene-Miocene rocks, labeled M, that have been split apart and offset by the fault. So look at here, we're looking for this color, we're looking for the letter M, right? Can you see they're right on the fault on one side and on the other side and nowhere in between, but they've been separated, and you can see the motion of the arrow would fit with the way that they've moved, huh? These rocks were formed at the same time, in the same place, but since they were formed, they've been broken apart and offset by the fault. And we can measure that distance, and using radioactive dating, we can find out how old they are, which will tell us how far they've moved in that amount of time. So that takes us here. Color the Pliocene-Miocene rocks red. So grab your pencil. I'm just going to use red stripes on mine. So show me that you can tell where those rocks are. And so what's going on is that these rocks were formed at the same time. They're a matching type of rock, but they were broken and offset by the fault. And what I'm thinking is that if we choose a point on them, I'm going to change my color to, how about, I think this blue will show up nicely. Oh, I didn't mean for that to happen. I wanted a new line. Okay. This right here at the very northernmost point of these rocks should be matching this point at the northern edge of these rocks, right? These two should have been together when those rocks were first formed. If we back up in time and move these arrows backwards, we should be able to imagine that these rocks are coming back together until they line up here. Go ahead and answer this question. How do the locations of these rocks compare with the direction of the arrows shown on either side of the fault? Are they matching the movement of the arrows, or are they going the opposite way and unrelated? Right. We can calculate how fast the plates are moving past each other by dividing the distance they're moving by the amount of time that they're moving. Now, anytime you measure speed, it's always going to be distance divided by time. And for us, distance over time. For us, what we usually think of as speed is miles per hour, right? MPH. Well, per means divide. Isn't miles a distance? And isn't hours a time? See what I'm saying there? Distance divided by time, miles per hour. That is distance divided by time. But we could also use other measurements, like in my physical science class, we are measuring forces and things like this, and we measure them in meters per second. Like how fast an object falls, we measure how many meters per second. Isn't that still distance divided by time? But because these things are so huge and because they move so slowly, we're going to measure how fast they're moving in centimeters per year. So a centimeter is about the width of your finger. And we're going to see how many centimeters they move in a year, because they're moving much more slowly than we drive, much more slowly than an object falls to the ground. So we can't use miles per hour, we can't use meters per second, but we can use a different measure of distance and time, centimeters per year, because they move slowly. So just keep that in mind. We're always going to be measuring these distances in different ways, but it's always going to be distance divided by time. Okay? And so what we're going to do is we're going to measure the distance between these two blue dots that I drew on here, because this is the matching part of the rock. Then we're going to use the scale down here to figure out how far apart they are in kilometers. But because these are very small objects, we're going to end up needing to change the kilometers to centimeters. So this is what I'm going to do. I'm going to get out a ruler, and I'm going to make this measurement on my computer. And hopefully, if this works, you should be able to see it. So I'm going to turn off my sharing of the screen. Come on. And are you seeing my computer screen now? Oh no, because I have the background turned on, huh? Let me turn off the background. And now you should see my computer screen, huh? Let me see if I can tell how good of a view we have. Sorry about that. Ah, that's better. Okay, so here's my my worksheet, and what I'm going to do is I'm going to take this ruler and I'm going to measure the distance between the blue dots. If we're doing this in class, we'd do this on paper. And I get about 10.5 centimeters. Okay? That's from one blue dot to another. Now that's not my answer, but I'm going to write it down just so I can remember it. 10.5 cm. What I have to do is change 10.5 actual centimeters to this distance scale down here. So on this scale, there's 6 1/4. So that's 200 kilometers to 6 1/4. And then I line up 6 1/4 with 0. I go to 10.5, and I'm getting just less than 150 more. So I had 200 plus, let's call it 135. What does that equal? Oh, that equals 335. So if I convert the 10.5 centimeters that I measured to this distance scale on the map, that means the blue dots are actually 335 kilometers apart, which is maybe 250 miles. That's going to go over here, 335 kilometers. And at this point, I'm going to go back to just sharing my screen again. Okay, so we measured from blue dot to blue dot. That was 10.5 centimeters. Then using the distance scale down here, the scale in kilometers, I figured out that that was 335 kilometers between these two places. And that sounds about right to me. To go from south of San Francisco to drive along Highway 5, not as far as Santa Barbara even, that sounds like about 335 kilometers, 250 miles. It sounds about right. Now,
Curly,
yeah.
I downloaded multiple different apps and none of them are working.
I don't know what to tell you. I have to keep moving forward with class. I am, like I said, I'm recording this, so you can come back to it later.
Yeah, okay.
Yeah. So keep trying is all I can say. It should have been whatever app you were using in the past, unless you've changed computers. At any rate, I've measured that from the top of this rock to the top of this rock that were once connected, they've now been broken apart and they've been offset by 335 kilometers. But I have to convert this to centimeters, and the way I do that is by multiplying by 100,000. So go ahead and do that. You're going to need a calculator here in a second, so pull up your calculator on your phone. You can do this on your phone right now, or maybe you know whenever you multiply by a number that has a bunch of zeros, if it's a 1 in the front and then zeros, all you have to do is take the number you started with and count how many zeros you have and add them afterwards. 5 zeros. Then I need to put a comma in every third one, and I get 33,500,000 centimeters. That's how many actual centimeters there would be between this point of these rocks and this point of these rocks. Okay? So, we found the distance between the rocks, how much they've been offset. Next, we have to find out how old the rocks are, so we can find out how many years it took them to move that far. And radioactive age dating shows that these rocks are 25 million years old. So all we have to do is divide the distance that they've moved by their age to find their speed. Distance divided by time, right? The distance they've moved in centimeters divided by their age in years. That's going to give us centimeters per year of movement. So I just take this number that I already wrote once, I just carry it down here, 33,500,000 centimeters. I divide that by the age of the rocks. Now be careful here, because I just wrote 25 and the word million, but now we need the number million. So that's going to be 6 zeros like that. Now this one I'm not going to do for you. You need to do this in your own calculator. 33,500,000. Pop that in your calculator, divide by 25 million, and put your answer in here. Okay, so when I've done this, I've found that basically it's about the same amount of distance as the word movement takes up on this paper. So it's asking you to use a ruler to draw a line that shows how far the fault moves in a year. And that would be this answer right here. But since we don't have a ruler to do that, we're just going to draw a line that's about the size of the word movement. Now, if this was printed out on paper, on regular paper, that would be about the movement that occurs in a year. So my question for you now that I want you to write about here is, what is your impression of the average speed of plate movement along the fault? What does that make you think of? All right, guys. So another way to look at this speed of movement is this is about as much as your fingernails would grow in a year. So the plate is moving at about the same speed that fingernails grow. Just creeping along, right? That's what we're looking at here. What's your impression of that speed of movement? Give me a thumbs up when you're ready to move on to the next page.
Do we write our answers to the question that you just asked on the paper?
Yeah, you should be filling all this stuff in on the paper as we go.
No, like, I know that, but like to the question that you just asked.
I'm sorry, what was that?
Like for the question that you just asked?
Well, right here, yeah. What is your impression of the average speed of plate movement?
Do
Right?
we write our answer?
Yeah, right here.
Okay.
You draw this little line, the same size as the word movement, and then you write your answer to that question. Thanks, Marisol. Okay. So we're going to move on. We've just calculated how many centimeters the plate moves in a year, and it's about this much if we were to draw it. That's how much those rocks are actually moving in a year. Great, thanks guys. So the thing is, it doesn't always move exactly this much in a year. The speed we calculated is the average movement. And this is over a huge span of time, over 25 million years. It's moved that much every year on average, but some years it might have moved 10 times as that. And then for 10 years, it might not have moved at all, and they would average out to being this much. Sometimes the plate moves much faster. Other times they hardly move at all. Now, if there was a sudden large movement along that fault where the rock moved, I don't know, 100 times this amount all at once, how would we experience that? How would we experience a sudden large movement of the rocks along the fault? The plate suddenly moves a bunch. What would our experience of that be? What do you think? Put your answer here. Shouldn't be too hard. If the land is moving underneath your feet, and you probably said that it was an earthquake. And as I was talking about earlier, one of the biggest earthquakes in US history happened near San Francisco in 1906. And it was right on that San Andreas Fault. And I showed you before I started the recording where that fence was torn apart, and you could still see it today. That earthquake is now thought to have hit at about 7.9 on the Richter scale. And this destroyed a lot of the city, first by the earthquake itself, but then a fire started and it couldn't be put out because water lines were broken by the earthquake. So they couldn't get water to the fire hydrants to put out any fires. This single earthquake produced an average offset of 5 meters, about the length of a car, all in a few minutes, a few moments. Imagine the land jumping that far all at once. All of a sudden, if you and your friend were standing on opposite sides of the fault, and all of a sudden you are a car length apart from the ground shaking underneath you. And that's why the plumbing got all torn up, so the water lines were broken and they couldn't put the fire out. I think it burned for like 3 days. So what we're going to do now is try to figure out how often an earthquake like that would happen in order for these rocks to be separated as far as they've moved. Okay? So we're going to try to figure out how often these big earthquakes could cause the fault to move this far. How far was that? 335 kilometers in 25 million years. How many big earthquakes would it take to move them? We figured out their average yearly movement. Now we're going to see what if all the movement was because of big earthquakes, the size of the San Francisco earthquake. How many would there have to be during that time period of 25 million years? So first, take the measurement we made earlier of the number of kilometers the rocks moved. And as I recall, that was 335. And now we're going to multiply that by 1,000 to change it to meters. So we have to convert the kilometers to meters. Oh, it's multiplying by a number with a 1 and a bunch of zeros. All I have to do is rewrite the number and the number of zeros that are there. Whoops, that's too many. Should be 3 zeros, it looks like. And then I need to separate them with my commas. 335,000 meters of movement. Now we're going to divide these meters by the 5-meter offset of the 1906 earthquake. This will tell us the number of big earthquakes that would be needed to move the fault this far. So what you're going to do is you're going to take this 335,000 down to here. Then you're going to take your calculator and divide by 5 to get the number of quakes that would have been required to move the land that far. How many big earthquakes would it take to move the land 335 kilometers if each quake is 5 meters? Since this is measured in meters, we had to convert our kilometers to meters up here first. Now you bring that 335,000 down here, divide by 5, fill in your answer here. Go ahead, use your calculator. 335,000 divided by 5. Lastly, remember that this movement took 25 million years. So you just found the number of earthquakes that happened during that time. I should say the number of big earthquakes that happened during that time. To find the average number of years between these quakes, in other words, how often do these quakes happen? Just divide the years it took to move the rocks apart by the number of quakes. So let's see, how many years were there? Oh yeah, 25 million. 25, and then we need 6 zeros since it's million. Divided by how many quakes? Well, that was here. So 25 million divided by your previous answer is going to tell you how many years happen between these big earthquakes. And then you're going to describe your impression of how often they happen. What does that make you think about? If they happen this often, is that as often as you would have expected? Less often than you expected? More often? What's your impression of how frequently those earthquakes occur? And that's this number here. How many years between the big earthquakes? We know that that one San Francisco earthquake moved the rocks by 5 meters. So how many earthquakes of that size would be required to move it 335 kilometers? That's what we figured out here, the number of earthquakes it would take, earthquakes that size, to move those rocks that far. And if we divide that into the number of years that have passed, we can figure out how often those earthquakes happen, how many years between big earthquakes. So what's your impression of that frequency of the earthquakes? Once again, give me a thumbs up when you're ready to move on from there. All right, thanks guys. So the next thing I want you to think about is we've calculated how many years between big earthquakes happen. And what I want you to think about is, does that number of years follow a regular pattern, or is it more random? Is it like the phases of the moon or a solar eclipse when we know in advance when it's going to be there? We know there's going to be a solar eclipse on this day. We can calculate that. It's a very regular pattern that we can figure out. Or is it more random, like a flood or a hurricane, some event that we're not sure when it's going to happen? And it kind of depends on a variety of factors when it does happen. So what do you think? Does the number of years between these big quakes follow a regular pattern, or is it more random? Are we guaranteed to have a big quake when this number of years you calculated has passed? So I don't know, maybe you got like 500 years here. Does that mean we're guaranteed to have an earthquake every 500th year? Think about this. If it was, I'm not saying that this is the answer, but let's just say if it was your answer and there were 500 years between big earthquakes, doesn't that mean that there should be 2 earthquakes every 1,000 years? Right? Doesn't that mean there should be 2 every 1,000 years if there's 500 years between big earthquakes? But does that mean that it will be exactly on the 500th year and on the 1,000th year? Or might it be on the 300th year and the 700th year? Or might it be on the 3rd year and then again on the 10th year and then nothing for 900 years? Wouldn't those still be 2 earthquakes every 1,000 years? So it could be any time during that 1,000 years that we have 2 earthquakes, but we don't know exactly when, do we? All right, the last question for the San Andreas Fault section. The average yearly movement on the fault is quite small, and there are many years between big earthquakes. Does this mean that residents in California have nothing to worry about from the fault? And please explain your answer and give me a thumbs up when you're ready to do the next section on Hawaii. Cool. All right, now, first of all, I want to apologize for not taking you on a field trip to see the San Andreas Fault or to see the volcanic islands of Hawaii. Maybe another day we can do that. At any rate, let's talk about how fast the plates are moving in Hawaii, and then we can compare that to our measurement along the San Andreas Fault and see if one's faster than the other or if they're pretty much the same. So first of all, some background. Unlike most volcanoes, the Hawaiian Islands are in the middle of a plate instead of along a boundary between 2 plates. Geologists think that Hawaii is above a mantle plume, which is the rising portion of a convection cell in the mantle. Geologists think that Hawaii, I already said that. These mantle plumes are thought to produce hot spots in the lithosphere above them, resulting in volcanic activity that can occur far from the edges of tectonic plates. Now, with the San Andreas Fault, we were looking at the movement along the edge of a plate. Now we're looking at movement in the middle of a plate, in the middle of the Pacific Plate. The theory of plate tectonics suggests that crust slowly moves across the stationary hotspots. As the plate moves, a series of volcanoes form one at a time, with the older volcanoes becoming inactive when a newer volcano takes their place. The older volcano gets carried away from the hotspot, and a new volcano forms over the hotspot in its place. The map shows the ages of rocks from the 5 main Hawaiian islands as measured by the decay of radioactive elements. Which is the oldest island? And which island is so young that it still has new lava hardening into rock? So over here is where the map is marking their ages in millions of years. And from that, you should be able to answer these two questions: which is the oldest island and which is the youngest island? Next question. What pattern do you notice in the ages of the islands? If you look at all these ages, what pattern do we see? Does this pattern support the tectonic explanation of the islands forming one at a time as the plate moves over a hotspot? Let's see. To support that, we would have to see that the islands are all in a line with the ages being in order, where we don't have like the oldest one in the middle of the line. We have them going in order from youngest to oldest. If they do that, that would support this tectonic explanation of the islands forming over a hotspot as the plate moves over it. And the last part of that question, it looks like you have 3 questions to answer here. Based on the map, where is the most likely location of the hotspot today? And before we start our measurements, I think we have one more set of questions to think about. Thinking about what lies beyond the map, what would this theory predict we should find further to the northwest? So that's going to be over here. What should we find up here in the northwest? And what should we find over here in the southeast? So make predictions about what you would expect to find northwest of the Hawaiian Islands and southeast of the Hawaiian Islands. And what I'd like you to do when you predict is to include what we call relative ages as part of your predictions. In other words, you have to tell me if it's older or younger than something around it. Relative age means you're comparing the age to something else. Absolute age means you're actually naming the number of years. You don't need to do that here. Just say if it's older or younger. So for example, if you told me that your sister is younger than you, but you didn't tell me how much younger, that would give me a relative age. On the other hand, if you said that your sister is 12 and you're 16, that would give me absolute ages. So these are absolute ages by giving you these numbers. We've given you absolute measurements of age. On the other hand, a relative measurement would be saying Oahu is older than Molokai. That's a relative age. So when you predict what you think is up here, include whether you think it's older or younger. Same thing over here. Predict what you think is down here and say if it's older or younger. Okay, so what I'm going to do is I'm going to measure once again, and if you can see my screen, you can see the red dots that I'm going to measure between the center of Kauai, the oldest island on here, and the point on the big island of Hawaii where active volcanoes are still erupting. And I found that those were 14.5 centimeters apart on my ruler. Now, when I compare that to the scale of miles, I have to go, let's see, that scale of miles was 250, and that was the first 5.5 centimeters on my ruler. And then I do it again, I'm up to 11 centimeters. If I do it twice, I have a line that's 11 centimeters long, but I need 14.5 centimeters, so I need 3.5 more, and that takes me basically to 150. Let me double check that. A little more than 150. We'll call it 160. So what I've done, the first time I did it, I took the camera down and showed you how I was doing it. This time, I'm going to measure this distance on this line. If you can see that on my screen, I've measured that. That was 14.5 centimeters long. And then I converted that to these kilometers. It took this whole scale twice plus this much more. Okay, so that's down here. I'm going to ask you to add these numbers together for yourself. In fact, I can just drag them down here for you. Go ahead and add those together. That's going to give the number of kilometers. But then we have to multiply this by 100,000 to change it to centimeters. So add these together in your calculator, and then multiply by 100,000, or take my shortcut of just rewriting this number and adding 6 zeros after, adding 5 zeros after it. And that does not count. If this looks like to me it's going to end in a 0, that doesn't count as one of your zeros. You need this number, including zeros, plus 5 more zeros, and you'll get the number of centimeters. Or, if you prefer, just multiply by 100,000 in your calculator. Then, we're going to carry this number of centimeters down here. We're going to go back to the map to find the age of the oldest rocks, which is right here. That was 4.7 million years old, not just 4.7, 4.7 million. So we have to write that as millions. That would be 4,700,000 years old. So whatever you had for centimeters, divide that by 4,700,000. That gives you the speed of movement at the Pacific Plate in Hawaii. Okay. So if we draw a line that's as long as that, it's a little more than half the width of this paper. So when you draw a line to show this amount of plate movement, it should be about, I would say, that long. So go ahead and draw a line about that long on your paper. And then answer these two questions. How fast is the Pacific Plate at Hawaii compared to the speed of the plates along the San Andreas Fault? Which one's faster? Or are they the same? Then make a hypothesis about their differences. And please include convection currents as part of your hypothesis. Remember, a hypothesis is just a possible explanation. It's a prediction that we could test. It's a thought question, basically. And then give me a thumbs up when you're done with that. Great. Good job, you guys. Okay. So, on this map, we can see the Hawaiian Islands again, but we've zoomed out and we can see that there are these other islands. Some of them are islands. Some of them are atolls, which are coral reefs on top of a sunken island. And then we're calling these as a group the Northwest Hawaiian Seamounts. And here I'm asking you for a definition of a seamount. I'm just going to give that to you real quick. I'm just going to call it an underwater mountain. Would be a seamount. Now, let's look at the pattern of seamounts across the ocean floor. Does it fit with the prediction you made earlier about what you should find northwest of Hawaii? Remember, I asked you to predict what you would find up here beyond Hawaii to the northwest and also beyond Hawaii to the southeast. What did you predict about finding up here? Did you predict that there might be more volcanic mountains out in the ocean? And notice the pattern that they make. Can you see that they're pretty much in a straight line? They're not really randomly distributed. They're pretty much a straight line. So, two things for you to write about here. What pattern do they make? And does it fit in with your earlier prediction? Okay. Now let's think about this. Out here, northwest of Hawaii, we've got all these seamounts, these underwater mountains. Some of them are small islands though, but there's no major islands here. They do have names. Some of them are big enough that there could even be an airport there. This was a really important one in World War II, the Midway Atoll. It's about halfway across the Pacific Ocean, which is why it's called Midway. What I'd like you to think about is, why are these big islands, whereas these are either small islands or they're completely underwater seamounts? There aren't any large islands out here, yet they're right in line with the Hawaiian Islands, suggesting that they're related to one another. And I want you to think of two possible reasons for this. Your first reason should relate to how they first formed. And if we think about these volcanoes going off, is it guaranteed that every volcano is going to build up to be tall enough to break through the surface of the ocean? That's one thing to think about. Secondly, another reason that they might be small islands or underwater mountains has to do with what happens to mountains as they get older. What happens to a mountain over time? What process is always acting on the landscape and carrying bits of the mountain downhill, in this case out to sea? What is that process that breaks down a mountain as it gets older? That has to do with number 2. Okay, so what do you think would happen if we measured the ages of these seamounts? Make a prediction. What do you think would happen if we did radioactive dating of each of these different islands and seamounts and atolls? How old would these rocks be, at least in comparison to the Hawaiian Islands? Again, you don't need to give me any numbers, but just tell me which you think would be older or younger, or if they'd be the same, and explain why you made that prediction. Now, further down on the page, I've actually given you another map that shows the ages of these islands. So what do we see? Basically, I'm going to zoom in on this. Here's the island of Hawaii, 0.4 million years old. Necker Island, 10.3 million years old, and it's 1,059 kilometers away from Hawaii. We're going to ignore the distance for now. Midway, 27.7 million years old. 38.7 million years old. 48.1. What pattern do we see happening? 56.2, 64.7. Could you describe the pattern as the farther you go away from Hawaii, what happens to the age of the islands? That's what I would like you to do here, where it says compare your prediction. Just describe the pattern that we see. The further we go from Hawaii, the what happens to the ages of the islands? Hopefully you saw that pattern in there. Now, there's another thing you're going to do in this section, which is I want you to think about how they make a nice straight line, but then right here, it makes a different straight line. They changed direction, didn't they? Let me make a straight line. I think this map is easier to see it on. There's that one. And then here's another straight line. What is going on with this? They made one straight line, they made another straight line, but they changed directions along the way. What do you think caused it to change directions? That's what I want you to write down here. I want you to think about what we studied before Christmas break and include an idea like hotspot, include plate tectonics, include convection currents as part of your explanation for why we see. We could also think of this as an arrow going from here to here, and another arrow changing direction right there. What's going on? Why did it change direction? What happened right here? Or should I say, not at this location, but at this time, somewhere between 38 and what is that, 48 million years ago? What happened there? Okay, we're almost done. 3 more things to do. So next, look up some information about a newly discovered place called Loihi and draw it on the map, not on the front of the page, but on this map. Okay, so you're going to add Loihi to this map, and I've looked it up for you. Here it is. This is the big island of Hawaii. And that would be the same as this island down here, huh? So I want you to add Loihi to this map. You can just use a circle to show its location, and then put a label on there too, okay? So here it is, it's right where, or you can use this triangle to show its location instead. And then label it Loihi. Incidentally, this says it is negative 980 meters. So that's almost 1,000 yards, almost a kilometer below the sea. It's almost a half a mile. Actually, it's more than half a mile below the sea. The top of this rise, you can see how the land is rising up here from the sea bottom to form the island of Hawaii. Loihi is right on the edge of it, huh? And it's still 1,000 meters, a kilometer below the surface of the sea. Meanwhile, Mauna Kea, the tallest point on the island of Hawaii, is 4,000 meters above sea level. That is actually higher than we are. That's about 12,000 feet. That's higher than Mount Rose, the top of Mauna Kea. Sometimes they can ski here. Go skiing in Hawaii. So add Loihi to your map and then come back to the question about it, which asks you what's happening there. So I'll just tell you, it is a new volcano that is forming underwater. It hasn't broken the surface yet, but there's lava erupting there on a regular basis, and it's gradually growing taller and taller. It might break the surface of the ocean and become a new island in the future, but it has 1,000 meters to go still before that happens. That'll be a while from now. But just like the other Hawaiian volcanoes, it's growing up little by little. And then discuss this. How does its location and activity compare to your earlier prediction of what we should find southeast of Hawaii? How does its location compared to what I asked you to predict you might find here? So you're going to answer that question. And then this one is kind of it's almost like a science fiction story that I'm asking you to write, or science fiction paragraph. What do you think the Hawaiian Islands will be like in 5 million years? 5 million years in the future, what do you think it will be like at Hawaii? Now, I want you to focus on their geology. You don't need to just talk about plants or animals or people, but what's going to go on with the geology? If we were to visit there in 5 million years, what would we find? And I want you to notice this island, Kauai, is about 5 million years old. So what do you think is going to happen 5 million years in the future? Will the islands still be located where they are today? Will some of the islands be eroded away? And if so, which ones? Might there be new islands forming? So that's what I want you to discuss to finish this whole thing. And then pretty much we're done with this assignment, and you should be able to upload it to get your points in the assignments.